Good afternoon. My name is Ronda Strauch, and I'm a graduate student at the University of Washington working with Erkan Istanbullu. So, mouthful. We're collaborating with Regina Rochefort at North Cascades National Park, so National Park Service, and exploring ways of estimating future peak flows. So we can use them for culvert design and also developing some tools to integrate that into culvert management for North Cascades National Park Complex. This works. So the motivation for this project stems from North Cascadia Adaptation Partnership, and this is a multi-agency partnership among 4 federal jurisdictions that share a common border and a vision to address climate change impacts that cross jurisdictional boundaries. So these 4 agencies, there's 2 national parks and 2 national forests that cover the north central part of Washington and the Cascade Mountains. And so at these workshops that this partnership had, they identified culverts as being one of the weakest links in managing their transportation infrastructure and being vulnerable to climate change. And then they also acknowledged that there was a lack of comprehensive information about culverts. And they sought to incorporate future projections in peak flows into their culvert management. So that's the motivation for our project. So why were some of these managers concerned about higher peak flows? Well, because we showed them maps like this and scared them. Not really, but this is concerning. So this is using the same data that Ingrid just told you about. And this is North Cascades National Park Complex. This is just against the Canadian border. And it's showing the 100-year flood return period change in the future in 2080s. So it's showing a ratio. It's just reflecting a ratio between what the Vic hydrologic model is showing in the 2080s compared to historical. So if it's greater than 1, that means there's going to be an increase in 100-year flows in the future. If it's less than 1, then it's not. And unfortunately, the entire park is greater than 1. And even some areas are showing, so it's not even across the park. Some areas are showing even more than a 2-fold increase in the 100-year flows by the 2080s. So this is definitely concerning for people who are trying to manage a network of roads and culverts. And so what are some of the drivers of why we might be seeing increases in peak flows? So I just wanted to touch bases on this. So in a warmer climate, we all know that warmer temperatures can hold more moisture. So that means when it does rain, it can rain at higher intensity. And also in this area, the projections are for higher precipitation during the winter. Less during the summer, which is nice for the summer, but higher in the winter. So this can also cause higher peak flows. And as Ingrid went through very carefully and very well, when we have warmer temperatures, we have more rain, less snow. So we get less snow accumulations. Those basins become larger. But we also have less spring snowmelt, which means that the peak flows will then shift earlier in the water year. And then there's a recent paper that just came out this year on atmospheric rivers. And so I just finished reviewing that, and it's found that atmospheric rivers are increasing in all seasons on the West Coast. And that means the intensity of rainfall and then the number of days we would have the atmospheric rivers. So that's just concerning.
Monica, can I just ask a tiny quick question? So, but that change in atmospheric rivers was not reflected in Ingrid's.
No, correct. It's just sort of like what could cause peak flows to be changing in the future versus what they are now or historically. So we wanted to explore different ways of how would you estimate peak flows in the future. And so when I'm talking about peak flows, those are a flow magnitude with a given return period. So I mentioned the Q100 in that scary map. That has a peak flow, or has flows that are occurring at 1% chance every year. So, but for a culvert, you might be looking at Q25 or Q50. So you could have different return periods that are still peak flows. And then these are typically estimated by streamflow records, but you don't have streamflow records everywhere. So you can also estimate these with hydrologic models, such as the Vic hydrologic model, the variable infiltration capacity model that Ingrid was talking about. And the beauty of using the modeling is that you can use it for the future. So the model projections that she talked about give us projections for the 2040s and the 2080s. So this is just to give you context for the study area that we were doing this project on, the North Cascades National Park, you can see it's a very rugged, very high mountain area. It's the Alps of the United States. And so we get really fast flow, fast runoff off these watersheds. And so that the VIC model information we have, the simulations, we were trying to use existing data. The whole point of this project was not to do new simulations and do new modeling, but to use what do we have already that we can use. And the Climate Impacts Group has lots of data that we can use, so we built off of that, what Ingrid was already doing. So we have a gridded product, that big Columbia Basin that Ingrid showed, that part of that covers the North Cascades. So we have that gridded product with 1/16 degree grid cells. And then we also have information on observations. So here are 3 watersheds that we have gauges on, right? We know what the historical flows are for those watersheds. So first we wanted to compare those. And that's what this is doing. So I said, okay, we've got these model simulations, how do they compare to observations? So these are the 3 watersheds, Thunder, Cascade, and Stehekin. Flow is on the x-axis and return periods on the y-axis. So our 100-year flow is right across the middle. And if you look at just Cascades, for example, the blue line is what you're getting from the VIC hydrologic model. This is at a daily scale. And so that estimates around a 6,000 CFS 100-year flow. If you go look at the observations from the gauges, it would estimate around a 12,000 CFS. And that's a daily scale. And then instantaneous is even more, 23,000 CFS. So we're like, okay, well the VIC model seems to be underestimating peak flows. So we have to do something about that. We can't just use them directly. And part of the reason that we think it's underestimating here is you saw that this modeling exercise was done for the entire Columbia River Basin. And it was actually calibrated for certain watersheds, but not these particular watersheds. So you could spend more time in the modeling effort and do better calibration to get it closer to the observations. But this is the existing data set we have, so we wanted to be able to use this data set at these locations. So how can we adjust these simulations that we have from modeling to more closely match those instantaneous peak flows? Because if I'm designing a culvert, I want to use sort of the worst case scenario. So the instantaneous would be, I want to get those kind of flows in my design. So we wanted to be able to adjust those VIC simulations to more match those instantaneous. So that's what we took different approaches to try to do this. So the first approach is, remember those curves? We're like, okay, maybe we can just transform our VIC simulation by just stepping through and stepping up to that instantaneous level. And we could just do that with a multiplier, do a ratio of the two. And that would mean you can just, at different peak flows, so that you could just multiply this multiplier by your VIC simulations. And then that would adjust it up to be more instantaneous. And then you could use this adjustment for those future simulations. So you get it would be more like instantaneous in the future. And it's a nonlinear relationship, so you have different multipliers for different peak flows, because that was a curve. And then it's different for different watersheds. So that was one approach that we could to adjust those VIC flows. Then we also wanted to try to use some of the tools that managers were already used to using. So we took a look at StreamStats. This is an existing tool that USGS developed in collaboration with Esri. That's a web-based tool where you can just go on the web, get your map, stick your culvert with where my culvert is. It draws the watershed for you that drains to that culvert, and it calculates. Is there a pointer? Here we go. Let me try this. It calculates here the peak flows. So here's your CFS. But that was quick. So okay, they like using these tools, so let's see if we can work with these tools. Because this is based on observations. The USG has developed regression equations based on where you're located, and they did by hydrologic region. So this shows you those regression equations. So we had those 3 watersheds that were at the south end of the park. And so 2 of them happen to be in a hydrologic region that's west of the Cascade Crest, and Stehekin is on the east side of the Cascade Crest. And then these are those regression equations that they have developed to estimate the peak flows at these different return periods. So we said, aha, maybe we can use this. Because the area right there, that's the area of the watershed. that's fine, but maybe we can use precipitation. Because that's mean annual precipitation is used to develop these regression equations. But we have precipitation that was used to force the hydrologic model, the Vic model. So we can take those forcings and use them in these regression equations and get new estimates of these different peak flows. So we tried that. So this is a comparison. The watershed scale, we've got a return period on the x-axis from going from 0 to 100-year return period. And these are the 3 different watersheds divided by those pink lines. And flow, the peak flow is on the y-axis. This first column is the observation. So those are those instantaneous estimates of peak flows from instantaneous records. The second column is from the stream stats, the regression equations. So this is what you'd get if you called up stream stats, put your culvert in, it would give you these peak flows. Third column is what stream stats would give you if you use those regression equations, but you use the precipitation forcings from the Vic hydrologic model in them. And the fourth column is that multiplier that we developed from the very, very beginning, was comparing the model results to the observations. So let's see how they compare. So on these two watersheds, Thunder and Cascade, are on the west side of the crest, and this is the observation. So stream stats looks like it overestimates or estimates higher peak flows if you use the stream stats for those western ones, but it's less. It actually is lower peak flows on each of the cascades. So let's look at our stream stats using the Vic precipitation. This is historical precipitation. It actually is fairly close to the instantaneous observed peak flows, both the western ones, but then you go over to the eastern ones and it's even lower. So the reason we're thinking it's lower on the eastern, maybe this is getting at one of your questions I think you might have asked, is the instantaneous records that you're getting, those can capture those kind of freak summer thunderstorms that'll occur just like over there and over there, but your rain gauge, your precipitation gauge may be over there and the rainstorm's over there, but the stream will still pick it up. So you can get big peaks showing up in your records that you're not going to get capture with the modeling. Even if you're using precipitation in your modeling that you're getting from precipitation gauges, doesn't mean they're at the same place that the stream gauge is located. So that was a watershed level. But like Ingrid's talking about, you're not going to put a culvert where it's like 23,000 CFS. That'd be a very, very big culvert. So we want to get down to the grid scale, small scale, closer to what you might be, the flows you might be having into a culvert. I'm not going to go through all these different methods, but I'm going to show you some examples of them. But I wanted to show you is that I had to have a new baseline. Because if I get to the grid cell, I don't have observations of my stream flow that I can compare my modeling to. So we decided to use those regression equations that StreamStats gives you with the precipitation from the Vic model, the historical, to develop as a baseline. Okay, here's where our baseline peak flows are going to be. So, but then we're going to compare it to some different methods for estimating the future peak flows. So this is one grid cell. We're going to compare the different methods. So this on the x-axis is the baseline. So this is stream stats with the Vic precipitation in it. And the y-axis is future peak flows based on a couple different methods, or 3 different methods here. Well, the first thing I want to show you is that everything is above the 1-to-1 line, which means that in the future, this is for Q2 all up to Q100. All of the different peak flows are all above the baseline. The second thing I want to show you is that there's more variability and larger changes in peak flows at the higher end, more towards the Q100 than at the Q2, the lower end peak flows. And then if you compare just one method, but 2 different time periods, this is 2040s and this is an estimate for 2080s. So it gets worse as you go further into the future. And so the different methods here, the first one, the lower one, the purple, is I call method 3, is using the stream stats equations, but the Vic precipitation that we used in the future, so future precipitation that's coming from the climate models. Method 4 is using the baseline and multiplying it by a ratio of future to historic coming from that precipitation data. And this was that ratio, that flood statistic that Ingrid talked about. So that's the middle one. And then the method 5 was using the multiplier that we developed in the very beginning, just from based on observations and modeling. And we applied that multiplier to the future. And that's the one that's actually the highest if we use that approach. So that was one grid cell, but they may not all behave the same way. So we wanted to look at all of the grid cells, but that are covering North Cascades National Park. So again, this is the baselines on the x-axis. This is for all grid cells, but I can't put all the different flows and time periods, so this is just for Q100 and the 2040s. And I'm showing peak flows on the y-axis. And I can only show 2 different methods because one of the methods, I only have the multiplier with the observations for where the watersheds were, and I had observations. I don't have it for the entire park. So the 2 methods that I was comparing are shown here. And the first one, that method 3, which was using those regression equations from stream stats and the future precipitation for the 2040s, shows you that about above a 1,000 CFS, everything is above the 1-to-1 line, meaning higher future 100-year flows in this case in 2040s. But there's no spatial variability. It's all on a straight line. So the other one, though, is where we use that ratio of future to historic stream flow projections from Vic. Multiply that ratio, so let's say the ratio is 1.5. Multiply that by the baseline, and then that gives me a point up in here. This is showing spatial variability within the whole park. So it's not on a straight line. So that is reflecting the added hydrologic processes that are in that Vic model. That's the benefit of using the Vic model. So how would we use this information to estimate future peak flows at a culvert? So what we want to get to is the magnitude, the flow magnitude. And let's say we're going to use Q100. We want that Q100. But we don't have it where here's our culvert. We don't have a gauge there. We don't know what it is. So most of our streams are ungauged. But we suggest doing that kind of analysis was using the stream stats, because it's a quick tool, and then multiplying the flows you get, the magnitude you get, by that ratio of the future to the historic that you're getting from the Vic modeling. And that will adjust it, in this case, in this area, up. But not all areas would have the same response. And we developed an easy tool to do that. This is building on what Ingrid had already done in Olympic. So over on your right is a map of the park, and this is the grids this is the Vic modeling grids overlaid on the park. And let's say you're a manager and I have a culvert that's located in this grid cell. It's grid cell number 89. Then I go over to an Excel spreadsheet, the same one that Ingrid showed you, put my grid cell in there, and it calculates a ratio of future to historic for different return periods, Q2 up to Q100. And it also produces these cool maps for us so we can see what the Q100 ratio looks like in the 2040s to the 2080s. And there's those red dots, which are different future GCM that we're using to force the Vic model. So you can see how much variability you have. And there's an average, and then the blue dots are the historic. You could also look I want to look at the Q100, look at the flow ratios for Q2 to Q100, but for this 2040s. So you can do it. But you can see a different pattern. Maybe at this grid cell, we're seeing that the Q2 has a higher change in the future than the Q100. You can go to a different grid cell and you could get a reverse pattern. So you have these cool graphs that come with this Excel tool. But the bottom line is you get this ratio, and then you go and use your stream stats tool. So you put your culvert in, it draws your watershed. This is Boston Basin in North Cascades. It estimates a Q100 of 909 CFS. So we just had a ratio of 1.23 for 2040s. So we use that ratio, multiply it by 909, so we'd get about 118,000 CFS. Yeah, 118, which is about 23% increase if you're using 2040s. If you're going to use 2080s, that's a 34% increase. So now you have your flow magnitude adjusted to be a representative of what the future might hold for that grid cell. And that's the smallest scales we can get. There was one other thing, that's my last tool, is remember folks were concerned about the lack of information they had on culverts. So we also developed a geospatial tool, not a spreadsheet, but it's a GIS tool. We did a basic and an advanced version. So this is in GIS, and we put all this information like you would go out with a data sheet, and you'd collect all this information. But you can now take your phone or your tablet, you put this geodatabase into Esri's collector app, and you can take your phone out. You can collect, okay, it's this culvert, this is where it is, this is its size, this is what it's made of, this is how the dimensions of it, this is what the stream's like, this is the slope. And, oh, I want to take pictures, so you take pictures of it, and it's all on your phone. Go back to the office, you download it. Now you have this geo-referenced information about culverts. But that's the beauty of this tool, and hopefully that we actually start maybe using it so we can get some good information about culverts. And then the maintenance folks come in and say, hey, I had a blowout on such a culvert, but now the culvert's a mile downstream. Well, you can go back and take a look at, well, what was there? And I just want to acknowledge that the part of this was paid for by the National Park Service, and then the climate data was coming from the Climate Impacts Group, the simulations, and then my time was supported by Northwest Climate Science Center and the National Science Foundation. Thanks. If you take any questions. Christopher.
So how did you inventory the culverts, or did you so in StreamStats you put in the point that you want to study, but how do you know that there's a culvert?
You'd have to know like on a map, like, oh, I know my culvert is like about right here, and so yeah, you would be estimating because you can't like see the culvert in the map that StreamStats provides you.
Right.
So yeah, no, we have an inventory. They do have some inventories, but in the Park Service, they have it on a FMS system, so it's a proprietary National Park Service, as you know, system, and it's not geo-referenced. They have like what road mile along the road it is, which I tried to put that in GIS, doesn't really work because you got topography to deal with. But this hopefully, if they want to use that app, and they are seeking funding for an intern for this coming summer to maybe try to test out using that app and going and actually collecting data. And then we would have that kind of information. Any questions? Any back?
Is the park using the tool?
No, that's why they just submitted a grant last week to try to get some funding to basically try to test some of these things, and maybe take that app out there and try to see if they can use it in the field, and see is there different information you want to collect than what's already in the app because there's a very advanced one that has a lot of different fields to fill out, but it really needs to be road tested, and then bring some other folks who are going to be using the information. Well, is this what you wanted to collect? Because you can easily modify it and put up different fields and stuff like that and collect different information.
I don't know if Dr. Eighth is going to talk about this, but increased sediment transport. When you have the snowpack going up and you have more flow, you're going to have more material going down.
Absolutely.
We're talking about precipitation, but the stream bed's going to get more full also.
Yeah, this is only dealing with flow. And so when the actual engineer who's trying to design the culvert here, this will give them like one of the key pieces of information they want to design their culvert. I want to know what I'm designing to a Q100 flow. Well, okay, at least I have that number, at least an estimate of what that number would be. Now I got to think, okay, what's above my culvert? What kind of stream bed do I have? Do I have an area that was burned, and so I have a bunch of trees, and they're all going to come down and get stuck in my culvert and completely block it? I'll have to take all of that into account before they'd actually make a decision on what they're going to do with that culvert.
Right, because every one of those culverts is a bottleneck.
Yep, absolutely, and there are a lot of them. So that the North Cascadia Adaptation Partnership, they managed collectively about 29,000 kilometers of roads and trails, and that's a lot of culverts, and they're not inventoried, so they don't necessarily know where they are. Yeah. Yeah.
I have a question. If there's time.
There's, yeah.
Okay. Are the engineers currently using StreamStats?
Yes, that's one of the reasons why we actually looked at it, because we were up there meeting with them, and they ran back there and they typed it and they went on StreamStats and came back like in 5 minutes later. Well, that area has got, because that was the map that you showed with the different grid cells. That was from one of those workshops. So yeah, they are actually using StreamStats.
Because I was wondering, so you had that comparison which showed that it didn't always agree with instantaneous flows, right?
Right.
So,
yeah, it's quick and dirty, but
yeah. So the culverts may not be actually designed for the situation they're in, regardless
right.
of climate change.
Yeah, it's true.
I guess what do you do about that? You don't have gauges, but I mean,
Yeah.
is that a reason for? I guess I'm wondering what you can do about that.
Well, it's the best information they have now without doing individual modeling. And there's nothing like going out in the field and looking at your particular culvert and then like, this is what it estimates it's going to be here. Does that look like, what does the stream channel look like? And
Is that I'm sure that's factored into like a margin of use.
oh, actually, that's more like what you might talk about, yeah.
Wait then.
On the margin of safety, yeah.
Stay tuned. Well, thank you, Ronda.
All right, thank you.